All right, so let's look at how to do the least squares linear fit. So again, we're starting with data that we varied x and measured y, and we can now tell if there's correlation using the correlation coefficient. And so what we'd also like to know is, how does y depend on x? What's the function to calculate y given an x? So this is called linear regression and also called a least squares fit. So again, it's easy to do. You've done this before. You can click on the data in Excel and add a curve fit line. Your eye is very effective at this. You can spot the trend. So if you have something like a clear plastic ruler, you can just set that on the graph and eyeball it and then find the slope and offset of that line. So that's an effective technique if you want to do something quickly. But in general, we're looking for an equation, a linear equation. So y is ax plus b, so we have a slope and an offset, where this capital Y is the prediction, given the measured x, what the y value should be. And we want to find the best a and b values, the slope and the offset, to make the capital Y's measure our measured y's. So best needs to be defined. What's the best a and b for this? So here's a picture of some data with x and y values that are measured, shown with the little x's here. And here's our curve fit line. And so we're looking at the deviation. So the error or deviation is the line y, the capital Y, minus the measured y. So again, you can see it right here. And so we'd like to minimize that error by choosing the best line. And so the most common way to do it is to square the error so that it's always positive and add it up over all of the points. So we're minimizing the sum of the squares. So here's the error squared, capital Y minus measured y squared. And if we use the equation for capital Y based on the measured x, we get this equation here. These are right out of the book. And so then we can call the total error the sum of the squares of the error. So it's this equation here. So this is what we'd like to minimize. So we can find the best a and b values to minimize our capital E. That's our best fit line. So to find the minimum, we use calculus, or we could use numerical techniques. In this case, we can solve for it analytically. If we find the partial derivative of error with respect to a at a minimum or a maximum, the derivative is 0. So we get this equation and set it to 0. Do the same thing for the minimum with respect to coefficient b, the error with respect to coefficient b. Get this equation, set it to 0. And we can solve them at the same time because it turns out that they're linear, and we can find equations for a and b. So these are just based on your measured data, your x's and your y's that you measure, and we have an equation for a and an equation for b. So this is the least squares best fit line, and that's the one that Excel gives you by default. So you'll probably never use these equations because it's built into so many programs. But here's an example of using the equations. So this is the same data that we used when we calculated the R value. So we've got x going 3, 4, 5, y going 7, 8, 9. So we knew it was 100% linear. We had an R of 1. And if we plug in here, we've got this equation for A. Looks kind of messy. This equation for B. If we write them out, we get n times the sum of xy, 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 minus the sum of x's times the sum of y's, sum of x's, sum of y's, divided by n times the sum of x squared here, minus the sum of the x's quantity squared here. So that gives us an a of 1. And similar kind of equation for b, it's the same denominator. we get 4. So that says that y equals 1 times x plus 4, and that makes sense. Y equals x plus 4. You can see it right here in the data. Or you could use Excel, or you could use MATLAB. Okay, so this approach, using the least squares approach to minimize the error between your fit and the actual data, is a common one, and it comes up in other places. So this is an example that's not in our book and won't be in the homework, but just to see how this applies to other things. Compass calibrations, if you have a 3-axis compass that measures the Earth's magnetic field. Here's a picture of how the Earth's magnetic field looks on the Earth. It has this magnetic field lines that look like this, and about where we are on the Earth, somewhere over here, this is a blow up. You can see the magnetic field is aimed north, but also into the ground with a pretty steep angle. So the idea is, if you measure the magnetic field on your drone, then if you face the drone parallel to this line, it should all be in maybe the x-axis. If you put the drone perpendicular to this line, the whole magnetic field will be measured in the y-axis or the z-axis. And so if you rotate this, the line stays still, but how it's found in the body coordinates of the drone changes. So to calibrate the compass, what's often done is you measure the magnetic field while you change the orientation of the drone. And if all the axes were equal, that vector would be constant and it would sweep out a sphere. But if the axes measure differently because they are scaled differently or because they're offset differently, then you won't get a sphere. So generally you're trying to find the offsets and scaling for all 3 magnetic axes that minimizes the difference to the sphere. So here's the error calculated for a compass calibration, a 3-axis compass calibration, where we have the magnetic measured minus this thing that we're solving for, the offset, divided by the scaling for the x-axis, y measurement minus the offset divided by the scaling, and so forth. So if it's a perfect sphere, this will add up to 1, so we figure that out, and this is the error that we would square and sum over all of the different measurements. So I don't have a video of the data I took with an airplane, but this is a common thing with all drones. So here's Captain Drone from YouTube calibrating the compass of a hobby drone.
That's good. Next thing you want to do is the calibration. So you tap on calibration, and it tells you to spin this baby horizontally like this. Once, twice, 3 times. I'm looking at my screen to see if it changes. Just there we go, it changed, and now you want to put it up and go once, twice, wait for the beep 3 times. Come on, beep, beep, beep. There we go. And then put it back down. That's it.
Thank you, Captain Drone. So this is some data that I took from a plane that I used to work on. It was called the MLB Bat 3. That company was bought by Martin UAV. But I did basically that same process with this airplane and measured the data, and then I ran my MATLAB script that I wrote that used that least squares process, and MATLAB has a built-in minimization routine to find the minimum error, and I used that to calibrate the compass. It was one of my jobs to figure out how to calibrate the compass on this airplane, and the manufacturer of the compass we used had a really helpful application note, so I copied their method and we used it for years to calibrate the compasses. Okay, so as a summary for the least squares fit, use Excel or MATLAB, that's your best bet. But you can get an idea of how it looks. Trust your eyes to make sure that the least squares make sense to you, and you should have no troubles.